In today's class, that is session 2 of module 1, we will discuss about the failure of gravity dam. So, in the previous session, we had discussed about the forces acting on the gravity dam, which are required to do the stability analysis or design of the gravity dam. So, let us see how all the failure of the gravity dam takes place. So, I'll share the content. So, the gravity dam is designed in such a way that it resists all the external forces acting on the dam, like water pressure, wind pressure, wave pressure, ice pressure, uplift pressure. So, these are the seven forces that we discussed by its own self weight. So, all the external forces are resisted by its own weight. Okay, so the if this is the dam section, this is the toe of the dam section, and this is the heel of the dam section. Heel. So this is the upstream side where there is water. This is the downstream side. So all the pressures, that is the water pressure, will be acting. The silt pressure, then other all the other horizontal forces, earthquake forces, will be acting in horizontal direction, whereas weight will be acting in the downward direction. So if you take moment about the toe, if you take the moment about this toe, so this will produce a clockwise moment, whereas this vertical force will produce an anti-clockwise moment. So these are called overturning moments. Overturning moments. Overturning moments. Whereas these are called resisting moments, which is in the opposite direction. The weight, the basically the vertically acting force will produce in anti-clockwise direction and it will resist the overturning. So the dam has a tendency to overturn like this. So this will it will tilt like this. It will tilt like this about this toe. So this overturning that is called overturning failure of the dam. Sliding. So there is friction developed here at the bottom of the dam between the contact surface between the foundation and the dam. Friction will be in the opposite direction of that of the horizontal pressure, water pressure. So if this force exceeds this friction, so there will be sliding. The dam will slide in this forward direction. Then compression by crushing of the toe material. Here the toe material will crush and it may fail by compression. And here the tension here the tension cracks will be developed near the heel. These are all the different types of failure of gravity dam. We'll discuss each one in detail. So first, next, let us go to the next slide. So, overturning of the dam. The horizontal forces such as water pressure, wave pressure, silt pressure, which act against gravity dam, causes overturning moments. As I already told, they cause overturning moment in the opposite direction. And to resist this, resisting moments are generated by the self weight of the beam. So, resisting moment will be in this direction, that is in anti-clockwise direction, whereas overturning moment will be in clockwise direction. If the resultant of all the forces acting on the dam at any of this section passes through the toe, the dam will rotate and overturn about the toe. This I will show you in the next slide. You can see here, this is the resultant. Let me take the razor. Yeah, this is the resultant. This is the resultant which is passing which is not passing through the base. It is passing away from the base outwards. So outside the toe of the dam, the resultant is outside the toe of the dam. In that case, the dam will tilt about this toe. The dam will tilt about this toe. If the resultant cuts the base within the body of the dam, there will be no overturning. So the resultant here should pass through the base of the dam like this. So if it passes through the base of the dam, if the resultant is like this, then there will be no overturning. Because the resultant is like this, it will overturn. The dam will overturn about the toe like this. Sorry, it will overturn about the toe. This is the dam. So it will overturn about the toe. So here there will be crushing of the material. So this is what is called as a overturning moment, and this horizontal force will produce moment in this direction, and this vertical force will produce moment in this opposite direction. So this is called overturning moment and this is called resisting moment. So if the resultant cuts the base like this, this is the base, if it cuts the base, then there will be no overturning. But if it passes away from the toe like this, that is outside the dam section, then there will be overturning. So there is factor of safety against overturning. The ratio of stabilizing moment divided by overturning moment, this value should be greater than 1.5, then there will be no overturning. So how do we get this sigma ms? Sigma ms is nothing but stabilizing moment. Stabilizing moment is the moment which will resist the overturning moment. Stabilizing moments are caused due to this. This is due to self weight and all other vertical forces, whereas overturning moment is due to this horizontal forces. Horizontal forces. So we will take the moment of all the forces about this toe and find out this factor of safety. We will work a numerical problem on this so you can understand it better. The next is uh, uh, next slide. So next failure is sliding failure of the gravity dam. Sliding failure of the gravity dam. When the net horizontal forces like water pressure, horizontal earthquake forces, and acting on the gravity dam at the base exceeds the frictional resistance. Friction resistance is produced by the body of the dam and the foundation at the bottom. Failure occurs, and this failure is called as the sliding failure of the gravity dam. So you can see here, so if this is the dam section and this is the base of the dam section, and here friction force is developed in the opposite direction, whereas the external forces is in this direction. That is, if this is the upstream side, water pressure is from left to right and friction is from right to left, and this is sigma v, sum of all the vertical forces. The magnitude of the developed friction will be equal to mu into sigma v, where mu is the coefficient of friction of the material in material at the base. So it is mu into sigma w, sigma v, sum of all the vertical forces is the friction developed. So this factor of safety against, if this horizontal force exceeds this resistance force, then there will be sliding of the dam in this towards the right side. Okay, so a dam will fail in sliding at the base or at any other level if the horizontal force causing the sliding are more than the resistance available to it at the level. If it is a high dam, this failure may take place at any height. For low dam, normally it is at the base. At the base, the resistance may be due to friction alone or due to friction and shear strength of the joint. Shear strength of the joint is considered when the dam height is more. Okay, that is for high dams. The friction alone is taken for low dams. The factor of safety is known as factor of safety against sliding, that is sigma mu sigma v divided by sigma h. This is frictional force. This is the resisting force divided by the force causing sliding, that is sigma h. The third failure is compression or crushing. So the dam may fail in compression when the compressive stresses exceeds the allowable compressive stress of the material, and the dam material may crush if it is made up of concrete. So concrete will have some allowable compressive stress. If the stress developed in the material exceeds this allowable compressive stress, the material will crush. Normally, this maximum compressive stress will occur at the toe of the dam, and this maximum compressive stress in the dam or its foundation is determined by theory of bending with thrust or eccentrically loaded. It is considered like an eccentrically loaded short column. I've shown it in the next slide. So how to calculate this compressive stress in the dam? So for that we have to determine an expression, and the dam is considered like a short column of width b and thickness 1, and this is 1. This is a unit length along the direction of the dam. B into 1 is the cross sectional area of the short column, and this is sigma v, vertical force, which will be acting at an eccentricity E. Okay, the and because there will be both direct stress as well as bending stress. This is an eccentrically loaded column. So direct stress, it is load divided by area. Load divided by area, load is sigma v. Load is sigma v. This is acting vertically downwards. Divided by area is b into 1. We have taken unit length of the dam. Dam will run for a longer length, but for design purpose we will take unit length. So sigma v divided by b into 1 plus stress, you can denote it by F or sigma, bending stress. So that bending equation we know m by I is equal to sigma by y or f by y, or f is equal to m by I into y. So m in I by y can be taken as z, that is a section modulus. You know this, so this will become m by z. So where z is equal to bd square by 6, because moment of inertia is bd cube by 12 and y is y by 2, distance of the extreme fiber. You know moment of section modulus for a rectangular section is bd square by 6, where b is equal to 1 and d is equal to b. So it is 1 into b square by 6. Here this dimension, the depth b is taken as d and this is 1. So substituting the values of b and d here, you will get 1 into b square by 6. So substituting that, so this will be, you see here, this is the direct stress sigma v divided by b into 1 plus m divided by I by y is written as z. I by y is written as z. And what is moment m? M is equal to this force into distance, sigma v into E. That is what is written, sigma v into E. E is the eccentricity of the force from CG of the cross section, divided by b squared by 6 is substituted for the value of z. So T is equal to sigma v divided by b is taken as common factor. It is in both the terms. So into 1 plus or minus 6. 6 will go to the numerator. 6e divided by b. Or we have this plus or minus because there is stress variation. At the heel it is less, and at the toe it is more. So it is sigma v divided by b into 1 minus 6e by b. Minus sign is used for determining the compressive stress at the heel, and for determining the compressive stress at the toe we are using a plus sign. So for no tension condition, so as I told you, there should be no tension, because the concrete is weak in tension, and normally it should be designed in such a way that no tension stresses should be developed in the concrete dam. Otherwise, tension cracks will be developed. Therefore, you will make this P as 0. So if you make this P as 0, So you will get sigma v divided by b into 1 plus or minus 6c by b. If you substitute equal to 0, this term is 0 or this term is 0. Sigma v divided by b cannot be equal to 0. So therefore 1 plus or minus 6e by b can be equated to 0, or 6e by b is equal to plus or minus 1, or e is equal to plus or minus b by 6. For no tension to occur from the center of the base of the dam. I've shown in the next slide. See, you can see here, from the center of the base of the dam at a distance of b by 6 plus b by 6 and say minus b by 6 and plus b by 6. That is for this distance, that is b by 3, for the middle third, I can say the middle third. If the resultant passes through the middle third portion, then there won't be any tension. So maximum value of eccentricity that can be permitted on either side of the center is equal to b by 6. That means the resultant must lie within the middle third. This is the outermost b by 3, and this is the this is towards the toe and this is towards the heel, and this is the middle third, and the resultant, if it passes through this middle third portion, then there won't be any tension. This you have to remember. So E should be less than B by 6. So we will just recall again. So it may fail by failure of its material, that is the compressive stress produced may exceed the allowable stress and the dam material may get crushed. So we have determined the expression for finding out the allowable stress, which is equal to sigma v divided by b into 1 plus or minus 6 e by b. A dam may fail if any of its part is overstressed, and hence the stress in any part of the dam must not exceed the allowable working stress of concrete. So you can see when the reservoir is full. This is the reservoir. When the reservoir is full, that is when there is water in the reservoir, the resultant will pass towards the toe. If the reservoir is empty, the resultant will pass through very near to the heel. This point you have to remember. So in both the cases, we should see that the stress should be less than the allowable stress for no compression failure to occur. So next, due to tension cracks. So we know that masonry and concrete are both weak in tension. That masonry and concrete gravity dams are usually designed in such a way that no tension is developed anywhere. So there should not be any tension. If there is cracks, seepage will take place, and further there will be failure of the dam. If these dams are subjected to tensile stresses, materials may develop tension cracks. So we should not allow any tension in the dam. So this is how the tension cracks will develop at the heel. At the heel, tension failures occur when the resultant strikes outside the middle third. That is, this is the base. If this is one third, and this is one third, and this is the middle third. If the resultant passes through this middle third, then there won't be any tension. There are two cases, as I told you, that is when the reservoir is empty and when the reservoir is filled. The dam gets cracked and loses contact. So when it loses contact here, there will be crack developed near the heel. Because water pressure is like this, it will tend to move forward or overturn. So this material will get crushed, and here there will be tension. Okay. So once the cracks are developed, it will lose contact with the foundation. The effective width, the dam width is B from here to here. From heel to toe is the total width. So once the cracks are developed, the width will get reduced. Width will get reduced, and in the formula which we derived for stresses, it depends upon this B. It depends upon this B. So B is inversely proportional to this stress. So if B is less, P will be more. P will be more. So what happens here? So B reduces In this case, the effective width reduces, therefore the stress will increase. The stress will increase. So if there is tension failure, the effective width reduces and thus the stress will increase, and further the material will get crushed. So it will indirectly cause compressive stress. So you can see here. So if the tension cracks are there, it will reduce the width, and again the stresses in the material will exceed the allowable stresses. So here you can see the dam gets cracked at and loses contact. Hence, effective width is reduced, which will result in increased compressive stress at the toe. So as I told you, when B decreases, P increases according to the formula, and this process goes on increasing and the crushing failure occur at toe. Hence, tension crack itself does not cause failure of the dam, but it leads to failure of the dam by crushing or by overturning. So, in this session 2, we discussed the different modes of failure of the gravity dam. The first one is due to overturning. We have to find out the factor of safety with respect to overturning. It should be greater than 1.5. And the second one is the resistance, the failure due to sliding. So here it happens when the frictional resistance at the bottom developed is less than the horizontal forces. So here also you have to find out the factor of safety against sliding, which should be greater than 1. And the third is the failure of the dam due to compression stresses. The compression stresses developed within the body of the dam should not exceed the allowable stresses. So that for that we have derived the expression, that is VB by B. P is, see, P or sigma, you can denote it as P or sigma. P is equal to VB by B into 1 plus or minus 6E by B. And the last failure is due to tension, and because of tension there will be cracks developed near the heel, and which will indirectly which will reduce the effective width at the base. And because B is reduced, and the stress in the toe will increase, and this will ultimately lead in the tension failure. So thank you.